So in this video, I'll go over some chapter 15 stuff, mostly this idea of the angle measurement radians, which is always kind of confusing, but it's actually really simple if you think about it, right? So I'll try to make it simple as I can, which should help you with chapter 15, the problem 15.3, and pretty much the rest of this chapter. It's just dealing with angles and the different ways to measure angles like radians, and then once you do that, then you can measure traveling in circles. Okay, so here's the idea. We have a circle, try to draw a circle here, and then we call this, of course, the radius of our circle. And it would be nice, let's say we go a certain, let's say we have an angle here, and typically we call the angle theta, Greek letter theta. And it would be nice to know if we're traveling in a circle, if we're moving in a circle, it would be nice to know this arc length, and they always call the arc length S. Yeah, I'm not sure why, but D would be kind of confusing because it's a circular distance. It's not a straight distance, right? We kind of go in this little arc. So it would be nice to have a relationship where if we knew the radius and we knew the angle, we'd know the arc length, right? Obviously, if the radius was smaller, then this would be the arc length. We would have a smaller distance. So S depends on the radius. And it depends on the angle. The bigger the angle, the bigger the distance we go. If we use degrees for that, then we'd say, okay, S is equal to R. So something has to do with R and the angle, right? Those are two things it depends on. So let's say we wrote down S is equal to R times theta. Well, if we use degrees, let's say the radius was, I don't know, 2 meters or something. Then the distance we went would be 2 meters times, and let's say our angle there looks like about 45 degrees, times 45 degrees, which is 90 meter degrees or something like that. Now if the radius is 2 meters, and this is 45 degrees, it looks like we probably went certainly less than the radius, right? Maybe we went, I don't know, looks like the distance might be a little less than 2. The way I drew it here. So we should get, it'd be nice if we just got what it was, right? Like 1.8 or something, but instead we get this 90 thing. And that's because degrees is kind of a random unit, right? We said how in the last video that 360 degrees is one circle. There's 360 degrees in a circle, and you could make up whatever you want. You could say 100 degrees in a circle. 360 works nice because you can divide it into so many pieces that we talked about, but still, it's just a random number. Okay, aliens might not be using degrees. I bet some would, some alien civilization out there, because, like I said, 360 is such a nice number. You can divide it in lots of pieces, but it's just a human-made random thing. It would be nice if we could just use this formula without having to worry about what unit we're using. Why don't we just use S equals R theta and measure theta in a unit that makes sense? So we can just, the distance you go is R times the number of new degrees. So let's redefine it. So if we go 1 degree, if we travel 1 degree in our circle, so if theta equals 1 new degree, so I'll just still call it a degree. If theta is 1 degree, then the distance we go, S, is equal to the radius. Wouldn't that be nice? Then we can just use this formula, that S is equal to R times theta. So instead of calling it degree though, because that's used, what they decided to do is call that a radian. So if theta is 1 radian, then the distance we go is R. And then we could just write, of course, S is equal to R theta. And it works for any distance we go. If we go 2 radians, the distance we go is 2 radii. So it works out perfectly if we use this new thing, this new degree, which they call radians because it has to do with the radius of the circle. So in a sense, radians are the natural unit because there's no units. You just put if the angle's in radians, you get the distance with the radius. You don't have to do any conversion factors. So it's the easiest thing to use. There's no conversion factors. Now let's say we go in a full circle. If we go in a full circle, then we know the distance we went was 2 pi r. So the distance we go, the arc length, is 2 pi times the radius, which then is r times theta, as we just said. Well, the r's are there, so therefore theta must be 2 pi. So a full circle then would be 2 pi radians, because the distance we go, of course, is the circumference of a circle is 2 pi r, and that would be, we said it was the distance we go, the arc length is r theta, so there are 2 pi radians in a circle, which means that 2 pi is the same as 360 degrees. So that's our conversion factor, 2 pi radians. You don't usually need to write radians, because if you're using radians, it doesn't matter, it's a natural unit. The units all work out. But to help you think, it's good to do that. So 2 pi radians is the same as 360 degrees. We can divide everything by 2. Or pi radians is the same as 180 degrees. Half a circle is pi. So that's our conversion factor. If you have degrees and you want radians, you multiply by pi over 180. If you have radians, you want degrees, you multiply by 180 over pi. Okay, whichever one you want, you put on the top. You want radians, you put the pi on the top. You want degrees, you put the degrees on the top. So pi radians is the same as 180 degrees. Okay, so the whole point of this again is if we want to know the distance we go, the arc length in a circle is just the radius times the angle, and if we use theta, if we use radians, we're done. That's the distance we go. If we use degrees, we got to change the degrees to radians. So let's say we know degrees, we go 30 degrees. Say, oh, we got to change that to radians, multiply by pi over 180. Degrees cancel, we did it right. So that would divide it by 3, get 6. That'd be pi over 6 radians. We can plug that in here. We know how far we went. Okay, now let's say we want the area of a wedge. Okay, so let's say we want the area. And this is like problem number 3. It has this, you figure out a lot of areas. So here's our circle again, and we want the area of this wedge, and we know that this angle is theta, and we can call this distance s, and this is r. Okay, well, let's see. We can just use ratios here. We know the full circle, the area of a full circle is pi r squared. And therefore, the area of this wedge is just a fraction of the full circle. But if we do theta in radians, then we can do a ratio here. We can say that the area, this area here, this is the area of a full circle, right? I'll put a special circle here, right? It's not the same as this area. This area we have here, compared to the full circle, we'll just set up a ratio, is the same as the angle we have, what fraction of angle we have, divided by the full angle, which is 2 pi. If the angle is 2 pi, we would have a full circle, right? Then this would be, we'd have 2 pi over 2 pi, we'd have pi r squared over pi r squared, and it works. But we have a fraction of it, and we have a fraction, our theta is a fraction of 2 pi. So the simple ratio, the little area we have divided by the full circle is the same as theta divided by the full circle theta, which is 2 pi. Okay, so we want a formula for the area. Multiply pi r squared times both sides. The area is theta over 2 pi times pi r squared. Let's see, the pi's cancel, which is nice. And all we have is a 2 in the bottom, so that's a 1/2. And then theta, and then r squared. Again, this only works for theta in radians, which is a natural unit. So we have our new formula here that the area of a wedge is just 1/2 theta in radians times the radius of the circle squared. So we're going to use that a lot. You use it in problem 15.3. Now what happens if we want the area, and this is what 15.3 says, we want the area of this little piece up here. So a little part of our wedge, well, that's not hard. This is like typical SAT problems. We don't have a formula for the area of this little thing, but all you gotta do is take the area of the big wedge minus the area of the small wedge. So we know what they'll tell you this radius, what that radius is. So what's the area of this little wedge here times, which is 1/2 theta times its radius. We know the radius of the big one, we just subtract. So the big wedge minus the small wedge gives us what's left over. So that's how you do section problem 15.3, and I think 15.4 and a bunch of them. You just use this wedge formula, again use radians, and it all works out really well. And then you can just subtract different parts, like the big wedge minus the small wedge, to get pieces of it. Okay, hope that helps, and good luck with these problems.